All right, so how you guys doing today? Good, perfect. It's Friday, right? Yeah. Good, perfect. All right, so let's start the what we discussed before on Wednesday. So we talked about the UV spectroscopy. So UV spectroscopy is we also gonna use some light in the spectrum where you can find the ultraviolet. It's a very kind of a wide range. You can define the UV in your light spectrum. But normally for this, our like an analytical chemical study, we normally use the one in 200 nanometer to 400 nanometer. So basically, if you have some conjugate pi electrons in here, we're gonna excite it to the higher energy level with the UV light. So if you expose to the UV irradiations, you're going to have this type of excitation happens. We call pi to pi star excitation, because literally putting electron on the upper higher antibonding energy level status, which is only possible when you had a UV eradication on the sample. So if that happens, obviously this will absorb certain amount of energy in form of the light, and then we're gonna try to make the amount of the observed light to analyze how many of those the conjugate pi system and how many of those compound is in the so if we do this, so we do once again A observance equal to log of incident light. So that light comes in. Light over when it passes through the sample with transmitted light intensity. Okay, so we're gonna do that to find out what might be the amount of observed light on the UV spectrum through the sample. Okay, so we can try to find that this one once again is laid about 200 nanometer. Oops, 400 nanometer. Okay, so here's one thing which I want to tell you. Do you guys wonder what I've been studying on and research-wise? What I was studying on was the virus, and I was just studying on this virus is made of DNA and protein. You know this, right? The biomajor, the virus is not actually it's not a living organism, but it's just more like a somehow kind of weird creature over there. But the DNA shows a 2.6 nanometer observance there, and protein is usually 280. I think you guys know if you took the bio lab, okay? So whenever I try to measure how much virus I made in the lab, we try to measure 269, because they two overlap into the bigger peak and the middle points. And I try to use the virus to treat the cancer, and also I try to use it for the stem cell bone regenerations, and also I try to use this one for nanotechnology. So I'm still working on few. Some of them are already done, but this is indeed very useful spectroscopy. We can actually find out how much of some compounds or even virus or any compound with the conjugate pi system. We can quantify it easily with this one. Makes sense, right? Okay. So whenever you do this one, observance once again is the same as log of this one, and we're gonna use it with a certain specific letter, Greek letter epsilon over here times concentration times path length. So this is the concentration. I know we have a different unit for concentration. In chemistry, we all know by now, it's just molarity. It's moles per liter. Moles per liter. And then path length is literally the length of the how long that the light will pass through. So we call this path length. That is why. And usually we put 1 centimeter. So that's the case. Have you guys ever done this in a biolab? You know how big your cuvette is, right? Cuvette is about 1 centimeter long. That is why. This is what we standard for the observers over here. So if you do this one over here, what you can get is the technically you can solve this one bit around to each other. So this will be observance over concentration times path length should be equal to your epsilon here. This is what we call molar observativity. Okay. So this is kind of a number you're gonna have for some standard conditions for concentration and the path length fixed in a certain compounds of observance value. So if you do this one, okay, maybe let's do. I'll give you some example here. So if you have if you do, let's do example here. So for example, if you have 0.37 is your A observance value you found on the UV spectroscopy, and you find that the concentration of that is about 2.7 times 10 to negative 6 molarity. So moles per, so it's moles per liter, and use 1 centimeter. Okay. So if you solve for this one, okay, you get about 1.38 times to the fifth. And then if you do this one, the unit will be this one. So this is, do you see this unit over here? Do you guys remember this? The observance is unitless because the intensity of the light over intensity will be canceled. The unit will be canceled. So you get this number, but this is a denominator of denominator. So this will be switched. Liter per mole centimeter. Because it's the, kind of makes sense. Because the moles per liter will be the liter per over mole, liter over moles per centimeter as well. So this is your value. So only thing you have to do is plug all the numbers over here, and you can get the number for molar absorptivity numbers there, okay, with that units. Makes sense, right? So if we have, but on the exam, I think I'll probably ask you to solve for this one, concentrations. So you might want to quantify using this fixed value that we're given in the table, and you're gonna see the observance number 2, and then I might ask you, oh, what might be the concentration of the sample then? Okay, so let's do it actually the other way. Okay? So if you have 1.00 times 10 to 5th, okay, it's the liter per mole centimeter. And then if you have 0.25, A, observance is 0.25, and you just need to put this one as X, and then I'll just give you just 1 centimeter as path length, so you don't have to worry about this one too much. And then you can just need to solve for X over here. Okay? Then you can tell me, oh, the concentration of this one is the X molar over here. So basically, what you can do is you can just try to flip these two over. So I'm just gonna make a reciprocal form of this one. So you can flip this two, okay? Because the X times 1 centimeter is the same as X centimeter. So then just flip this one over, X over 0.25. Okay. So if you do this one, you know this one, right? That's 5 times negative 1. So it will become 10 to negative fifths will be equal to x over 0.25. So this one is a fractional number, so make it easier. So you can multiply by 4 on top and bottom, still be the same number because it's a fraction number. So that makes the 4x over 1, which is just the 4x, should be equal to this over here. Right? Okay. And then to get x, you just need to divide by 4 and 4. So your x will be 2.5 times 10 to negative 6. One more. So this will be on your exam. I think because usually those epsilon bullet objectivity numbers will be given in the table because we know it's a standard conditions. And once you measure the observance value, you'll be able to know, oh, this is a concentration of protein or DNA or compounds. So this is more practical this way because that's what you're gonna do with the. You already did probably in the biolab too. Okay. Can I move on? Okay. All right. So if that is the case, we're finally done with this chapter. All right, so let's move on to the next chapter, I think chapter 15. We're gonna talk about mostly benzene, or you can say aromatic compounds. So whenever you think about this, the aromatic compounds with the aromaticity actually comes from some very pleasant smell. Like you have some fragrant compounds that gives very pleasant smell, like cherry or pear or other fruits. It all came from this compound. So if you look at this one closely, it has a ring with the 3 double bonds. So it will be well conjugate. So this is more like so you know this is benzene. This is benzene, right? And then this is like a benzene-like ring attached to this one, which is your aldehyde. This is a carbonyl group with the hydrogen. And this is a benzene. So this is what we call benzaldehyde. It's just the benzene, like the ring attached to aldehyde, so benzaldehyde. So this is the one that gives us quite a pleasant smell there, and the fruits too. And as some plant, we had some fragrant compound looks like this. So you have just one methyl group on your benzene ring structure. This is also what we call toluene. Okay. Then also you smell a lot of weird smell. Have you ever smelled from the gasoline or your coal or petroleum? You have a kind of weird smell comes to this coal and the fossil fuels, right? Because of a lot of benzene related compounds are all there. But initially we thought that there was the one that gives us quite pleasant smell. So we start using aromaticity in that way. But if you move on to those two fossil fuels, you have a lot more benzene ring related compounds. So we're gonna talk about this chapter. Okay. So if you look at the spectrally fossil fuel coal, you have a lot of those type of compounds. So we're gonna look at the several things. So we have obviously this is benzene, okay, and you have some weird one looks like this. This is the inulin. Okay. And then we have some bicyclic benzene. This is the naphthalene. Okay. We have 3. My drawing is not so good today. Okay. So this is what we call anthracene. We have some more. It looks like this. Okay. This is what we call biphenyl. Oh, sorry. Okay, biphenyl. And then we have another one. So it's not just that. There's so many things just like this in this way. Okay, so we also have this this one. This is what we call phenanthroline. Okay, so as you can see, we have a lot of different types of compounds. Looks like this too. Okay. Okay. So this is okay. Yeah. Let's copy it sometime. So this is a lot of the benzene-like compound you can find in the coal. You can also find this in the petroleum too. But as you know, petroleum is mostly alkane, which is better for burning into the engine or other power source. So it can use a bit more in a high energy. But when you process the types of alkane in the petroleum, you have also some benzene-like compound coming out after chemical processing. So you may see after process the petroleum, but mostly even just natural coal, those type of different type of benzene ring compromised compound is very common here too. Okay, makes sense, right? And then interestingly, the aromatic compounds with the benzene ring structure can be also found in the body too. So this is the estrone. This is kind of minor version of estrogen, which is a female hormone. So as you can see, unlike other typical steroid, it has also benzene ring structure over here, which is quite also important in the body regulation too. And there's some compound. Looks like this. Okay, it's quite long. Oh, I don't have space here. I'm sorry. Sorry, there is no space, but I'm sorry, there's no this is off. I'm sorry, but this is Lipitor. This is a medicine to control your cholesterol level in the blood vessel. So this is also, you see a lot of benzene-like structures there. So it is important to understand those type of compounds with the aromatic signature. Okay. Okay. So there are a few more things we can do with the nomenclature. So before we hit any part of nomenclature, let's try to hit a little bit of fundamental base first. Okay. So as you know, you can do benzene. So you can always start with the benzene to start the name with. So this is benzene. If you put the one methyl group over here, guys remember it's a toluene, right? Toluene. If you put two, we call this xylene. If there are two, so you can put it here, or here to here, or here to here. So if you put it here to here, okay, there's just three possible ways to do it, right? This one, right? If you have a two, there's 1, 2, and 3. Okay. So if that is the case, this is what we call the, author position. It's just right next to each other. So 1, 2. Okay. This author xylene. If it is somewhere between, it's what we call meta xylene. Okay. And if it's on the totally opposite side, so we call para xylene. So technically speaking, you can also name it this way. You can always say, either you're saying orthoxylene, you can say 1,2 dimethylbenzene, that's okay too. But once we have a really good way to say it in just one, one compound name, you can just say orthoxylene. That explains everything anyway. So this is something you can do. Makes sense, right? So and then if you change the hydroxy group here, so this is a hydroxybenzene, right? So hydroxybenzene, you can call this phenol, because the reason why they call this phenol is if you try to break it from the functional groups, if you have a benzene ring attached to a certain base, this is what we call phenyl groups. So for example, if you have octane, you have octane, right? If you have a benzene ring is attached to it, if you have a benzene ring attached to it, you can call this 2-phenyl octane. So this is like your group, okay? But now you put it in the hydroxy group, right? Which is alcohol. So we have OL over there. Phenol, okay? Makes sense, right? Okay. So if that is the case, let's make it a bit bigger. So if you have, because you did this one, it's a benzaldehyde, right? But if you try to change this one to carboxylic group instead of aldehyde, there will be IC acid for this carboxylic group name. So it would be benzoic acid. Benzoic acid. Because this is a carboxylic group, not aldehyde. Makes sense, right? See do you know do you guys like Diet Pepsi? You do? No? So you're drinking this one too. Technically, I hope you guys remember this from the Olga 1 lab. Do you guys remember this? This is benzoate. It's more like an ester group over here, right? And this negative charge on here will pair with the potassium ion. This is what you're drinking in the Diet Pepsi. So they call it potassium benzoate. Okay. All right. So just a little more. If you have, I know it's a lot to memorize at once, so I'll do this again on Monday. Don't worry about it. Okay. Okay. If you have ketone groups over here, we name this one acetopenon because it's a ketone. It looks like an ester groups there. Okay. So acetopenon. All right, we're almost done. We're almost done. Okay. We're almost done. I promise you. So if you have this one. We call this styrene with one double bond conjugate into your benzene ring. We have a quite special name for this one. It's styrene, which is, if you guys remember this is the one you're going to make polymer, which is a styrofoam. So we call this styrene. Okay? It's the styrofoam with the ENE. Yeah. So that's it. Yeah, I promise. That's pretty much good. Let me think actually more. There's some more. Oh, I'm sorry. There is one more thing. There's one more. I'm sorry. There's one more. Is this one with the amine groups. So it's a aminobenzene. You can call this aminobenzene with aniline. This is also something you can use, like using the phenol or the acetopenon and so on. This is also the same thing. All right, so kind of makes sense. It's just some time to memorize those names because we have some special benzene compound has a special name. Those are pretty much everything, I believe. So I'll move on. But it makes sense, right? Just okay. So let's move on. So if you have that, you can try to use it for actual nomenclature now. So you know all the base now, right? You have all the base name. You can actually use it for certain actual practical problem over here. So when you try to name this one, it will be so hard because you have one methyl group here and 3 nitro groups over here. So maybe it's too much. But if you remember, we tried to name this base as what? Toluene, right? So then you need to number those 3. It'll be easier to name now. Okay? So that will be toluene is always start from here because this is the way you have a methyl group, you call it toluene. So then you start from 2, 3, 4, and 6. So there will be 2, 4, 6, nitro toluene, not benzene, right? Because your base now is toluene, not benzene. You could possibly do it with the benzene, but it will be very weird because we have a base name which is toluene, which is better to name with those nice 3 same groups there. Okay. All right. Okay, we got a few more. Okay, so how about this one? And this one. Okay. So once again, you can always do that with the some combinations like one, two, well 2 hydroxy. That will be also kind of a weird because now you know what this one, which is what let me remind you, it's phenol, right? Okay. Now you only need to add those 2 as a prefix because now you have an even bigger base, which will make your nomenclature much easier. So it will be 2, 3, 4, 5, right? 2, 5, dimethyl, okay? And then just that, right? Phenol. It's much easier this way, right? Because you have now the one that has the much bigger base name. Then you have only a few same prefix groups attached to your name. Okay. That's pretty much it. Okay, let's do one more. Let's try this one. Okay, so in this case, we know what this is, right? Which is the benzoic acid. So there will be benzoic acid. And then now you only have one group attached to it, which is chloro, right? So you have a chloro groups over here. So it's a chlorobenzoic acid here, but the position of these two is the para position. So we call this para chlorobenzoic acid. So then maybe if I change this position to here, what could be the name there? It would be, it's ortho, meta, para, right? So in this case it would be meta. Yeah, perfect, that's it. You guys did really well today. Makes sense, right? I know it will take some time because we went through a lot of numbers of names. I totally understand, so I'll definitely do this again with the practical problems on Monday. But it is important to know what is the actual base in your whole compound that makes it easier for you to understand the later topics in future. All right, so that is the case. Now we wonder why does the aromatic city or the aromatic compound with the benzene-like structure is so important here. So when they try to brominate your benzene over here, there's some ions over here. They could do this one. But how hard they try, they couldn't do this one. Which you can do, if you remember this one right, you could do this with the alkene and alkyne, right? But this one was not possible, only up to here. So the chemist now thinking, oh, there must be something on this benzene ring-like structure. There got to be something there to make this reaction different than others. Okay. So if that is the case, they also did measure the enthalpy change of hydrogenation. With your base is cyclohexane, which is no double bond in any part of your ring structure. But you have a 1 over there. Okay, there was the energy gap between these two was the 118 kilojoule per mole. And you have some conjugate diene ring structure, which is slightly lower, as you can assume from the diene we learned before. It wasn't ring structure, but it's slightly lower than just the double amount of this one, was about 230 kilos. And the chemists were actually thinking about, oh, maybe three pi bonds, 3 double bonds will make even harder to do it. Okay, so then we have a benzene ring over here. So this is the number they estimated. Like, oh, this might be the number because it's going higher and higher and higher, right? It was even lower than the second one, was 206 kJ/mol. Meaning, it's pretty much the same we learned in previous chapter. Meaning, this one is more stable, much more stable than these two. So there was just something going on with this, the 6p orbital conjugation over there, like we learned in Diane, but it's more dramatic case that will give us even very, very good stability. So energy gap between here is very small because they're already quite stable there. They don't have to put a lot of energy to anything to be even more hydrogenated. So this is why. This is simply because of the stability of the benzene. So we're gonna do that with the 6p orbital energy diagram maybe on Monday. But it's slightly more complicated than ones we did in last chapter was the Diane. But it's pretty much the same actually. It's just slightly different.